You look around this room, there are electrons everywhere, in your body, in the walls, in the air, in every atom in the entire universe. We estimate there are something like 10 to the 80th power electrons in the observable universe. That's a 1 followed by 80 zeros. That's more electrons than you can possibly imagine. And here's what's really strange about them. Every single one of these electrons is absolutely identical. Same mass, same charge, exactly the same. You can't tell one electron from another. It's not like people where you can say, oh, that's Bob and that's Sally. No. All electrons are completely indistinguishable. So Wheeler's asking why? Why are they all the same? And his answer was beautiful and crazy at the same time. He said they're all the same because there's only one electron in the entire universe. Now you're probably thinking, wait a minute, Feynman, that's nuts. I just told you there are 10 to the 80th power electrons, and you're right to think that. But let me explain what Wheeler meant, because it's really quite remarkable. To understand this, you need to think about space-time. Not just space, not just time, space-time. When we draw a diagram of space-time, we put time going up this way and space going across. And when a particle moves through the universe, it traces out what we call a world line. It's like a thread running through space-time, showing where that particle is at every moment in time. Now here's where it gets interesting. An electron moving forward in time, that's just a regular electron. But what about an electron moving backward in time? What would that look like? Well, it turns out that an electron moving backward in time looks exactly like a positron, the antimatter version of an electron, moving forward in time. Same mass as an electron, but opposite charge. This isn't just philosophy, this is real mathematics. When I developed my theory of quantum electrodynamics, this idea became incredibly useful. In my diagrams, I could represent a positron as just an electron going the other direction in time. So Wheeler said to me, suppose the world line of this one electron, instead of just going forward in time like we usually think, is actually this tremendous knot, going forward, then backward, then forward again, backward, forward, backward, all tangled up across all of space-time. Imagine you're looking at a piece of cloth, and you take a needle and thread, and you push it through the cloth, then back down, then up again, then down again, hundreds and hundreds of times. If you look at the cloth from above, you see all these dots where the thread comes through. But it's all the same piece of thread. That's what Wheeler was suggesting about the universe. Take a slice through space-time at one moment, what we call now. You'd see this world line of the one electron crossing through that slice maybe 10 to the 80th times. Half of those times it's going forward in time. Those are the electrons. Half the time it's going backward in time. Those are the positrons. But it's all the same electron. I mean, think about how elegant that is. You don't have to ask why all electrons are identical anymore. They're identical because they're literally the same particle, just seen at different points along its enormously complicated journey through space-time. But here's the thing. I told Wheeler, well, Professor, that's a beautiful idea, but there's a problem. There aren't as many positrons as electrons in the universe. And that's true. We see electrons everywhere, but positrons, much rarer. If Wheeler was right, if every electron going forward in time is matched by the same electron going backward as a positron, then we should see equal numbers, but we don't. Wheeler, he wasn't stumped. He said, well, maybe the positrons are hidden in the protons or something, but that didn't really work. I mean, you can't just hide half the particles in the universe somewhere and hope nobody notices. The numbers don't add up. So I didn't take the idea seriously as a literal description of reality. But here's what I did take seriously, and I stole this from Wheeler. The idea that you could represent a positron as an electron moving backward in time. That insight, that mathematical trick, that was gold. Let me show you why this matters. When you're trying to calculate what happens when particles interact, you draw these diagrams. I developed these diagrams, people call them Feynman diagrams now, and they're incredibly useful for figuring out probabilities of different quantum processes. In one of these diagrams, you might have a photon, a particle of light, and it creates an electron-positron pair. The photon disappears, and suddenly you have an electron and a positron. Then they meet each other again and annihilate, creating another photon. Now, I could draw this as two separate particles being created, moving around, then destroying each other. That's one way to think about it. But there's another way. You could say there's just one electron. It's moving along, absorbs a photon, which kicks it backward in time. Now it's a positron. Then it absorbs another photon, which kicks it forward in time again. Now it's an electron again. Same process, same mathematics, but a completely different way of thinking about it. And this isn't just playing with words. When you use this idea that antiparticles are particles going backward in time, the calculations become simpler, much simpler. Instead of having to draw separate diagrams for every possible combination of particles and antiparticles, you can combine them. One diagram does the work of several. This was crucial for developing quantum electrodynamics, the theory of how light and matter interact. And it works. The predictions we made using these methods agreed with experiments to incredible precision, 9 decimal places in some cases. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. Now, Ernst Stueckelberg, a Swiss physicist, he actually had this idea before Wheeler talked to me. He thought about positrons as electrons going backward in time in the 1930s. But somehow I didn't know about his work when Wheeler called. Wheeler's phone call is what got me thinking about it, what got me to build it into my formalism. Let me tell you what's really beautiful about this whole thing. Even though Wheeler's one-electron universe probably isn't true, literally true, there's something deep there. Every electron is identical. We can't put little tags on them saying this is electron number 42 and this is electron number 1,938,472. They're fundamentally indistinguishable. And in quantum mechanics, that indistinguishability isn't just a practical limitation. It's not like we just can't see the differences. There are no differences. And that fact, that deep sameness, has real consequences. It's why chemistry works the way it does. It's why materials have the properties they have. The whole structure of matter depends on electrons being truly identical. So maybe Wheeler was onto something after all, even if his specific idea doesn't work. Maybe there's a sense in which asking which electron is this is the wrong question. Maybe electrons aren't individual things that happen to be similar. Maybe they're more like ripples in a field, waves in the ocean. You don't ask which wave is this. A wave is just a pattern moving through the water. We think now in terms of quantum field theory. There's an electron field pervading all of space, and what we call an electron is an excitation of that field, like a ripple. The field is fundamental, not the particle. And in that view, all electrons are identical because they're all just different ripples in the same underlying field. But I want to come back to Wheeler's idea for a minute, because even though it's probably wrong, it's beautiful. Imagine it were true. Imagine there really is just one electron weaving back and forth through all of time, creating the appearance of countless particles. That would mean the electron in your hand and the electron in a star 1 billion light years away are the same electron, just at different points in its journey. It would mean that in some sense everything is connected, literally connected, by this one thread running through all of space-time. And here's something even stranger to think about. If you had an electron that's part of your body right now, and if Wheeler's idea were true, then sometime in the past or future, that same electron, traveling backward or forward through time, might have been in Julius Caesar's body, or in a dinosaur, or in a star that won't be born for another 1 trillion years. There's something almost mystical about that. This one particle experiencing every electron's journey through time all at once. From the perspective of that particle, it's not making countless journeys. It's making one journey, an incomprehensibly long, tangled journey, but one journey nonetheless. Of course, this raises all sorts of questions. How does the electron know to turn around in time? What makes it bounce backward? Wheeler suggested its interactions with photons that could do this. An electron absorbs a photon, and that interaction reverses its direction through time. But the mathematics of exactly how that would work is, well, it's problematic. And there's another problem. Time has a direction. We call it the arrow of time. Things happen in a sequence. Eggs break, they don't unbreak. Coffee cools down, it doesn't heat up spontaneously. Entropy increases. That's the second law of thermodynamics. And it's one of the most fundamental principles in physics. An electron moving backward in time would be experiencing a reversed arrow of time. From its perspective, broken eggs would reassemble. Coffee would spontaneously heat up. Now, for a single particle, maybe that's okay. The laws of physics for individual particles are time reversible. But when you start thinking about real physical processes, about thermodynamics, about causality, it gets messy. If I do something to an electron now, and that electron is really a positron going backward in time from the future, then in some sense, the future is affecting the past. That bothers people. It bothers me. Causality is important. Effects should come after causes, not before. But you know what? Quantum mechanics is already weird in ways that challenge our intuitions about causality. We have entanglement, where measuring one particle instantly affects another particle far away. We have the uncertainty principle, where you can't know both position and momentum precisely. We have particles being in multiple states at once until you measure them. So maybe we shouldn't be too quick to dismiss ideas just because they seem strange. Physics is strange. The universe doesn't care about what makes sense to us. Still, the one-electron universe idea has that one fatal flaw. We don't see equal numbers of electrons and positrons, and nobody's come up with a convincing explanation for where all those positrons would be hiding. The universe is mostly matter, not antimatter. That's an observed fact, and Wheeler's idea doesn't explain it. In fact, that asymmetry, the fact that there's more matter than antimatter, is one of the great mysteries of physics. We don't really understand why. The laws of physics, as we understand them, treat matter and antimatter symmetrically. They should have been created in equal amounts in the Big Bang, and then they should have annihilated each other, leaving behind nothing but energy. But they didn't. Somehow, there was a tiny excess of matter over antimatter. Maybe one extra matter particle for every billion matter-antimatter pairs. And that tiny excess is everything we see. Every star, every planet, every atom in your body exists because of that small asymmetry. So Wheeler's idea, beautiful as it is, doesn't help us with that puzzle. In fact, it makes it worse because it predicts exactly equal numbers of electrons and positrons. But you know what Wheeler's idea did do? It changed how we think. It showed that you could take a completely wild idea, something that seems crazy on the surface, and find something valuable in it. The one-electron universe might not be real, but the concept of antiparticles as particles moving backward in time, that's real. That's in the standard formalism of quantum field theory. That's how we calculate things, and that's how science works a lot of the time. You have a crazy idea. You play with it. You see what works and what doesn't. You steal the good parts and discard the rest. Wheeler gave me this idea, and I stole the best part of it, and I used it to build something that actually works. That's what I want you to understand. Science isn't about being right all the time. It's about exploring possibilities. It's about taking ideas seriously enough to work out their consequences. Sometimes you find out your idea is wrong. That's fine. That's progress. You learned something. Wheeler knew his idea probably wasn't right. He wasn't claiming to have solved everything. He was exploring. He was asking, what if? And in that what if, he found something beautiful, the image of the universe woven together by a single thread, forward and backward through all of time. Even if it's not literally true, there's truth in it. Not factual truth, maybe, but a deeper truth about the interconnectedness of things, about the fundamental sameness of particles, about the strange, counterintuitive nature of quantum reality. And there's another thing this idea teaches us. Humility. We think we understand time. Forward, backward. It seems obvious, right? But maybe it's not so obvious. Maybe time is stranger than we think. After all, in relativity, time and space are mixed up together. What's time for me might be partly space for you if we're moving relative to each other. Simultaneous events for me might not be simultaneous for you. So maybe asking whether the one-electron universe is true is asking the wrong question. Maybe the question is, does this way of thinking help us? Does it give us insights? Does it suggest new calculations, new experiments, new ways of understanding? And the answer to that is yes. Absolutely yes. This idea, this wild, beautiful, almost certainly wrong idea, led to real progress in physics. It led to the Feynman diagrams. It led to quantum electrodynamics. It led to calculations that agreed with experiment to astonishing precision. That's the power of imagination in science. You don't need your ideas to be right. You need them to be interesting. You need them to lead somewhere. Let me tell you one more thing about this. There's something poetic about the idea that every electron is the same electron. It means that in a deep sense, we're all connected. The electrons in your brain, the ones carrying the signals that let you think and feel and understand what I'm saying, those electrons are fundamentally identical to the electrons in every other person, in every star, everywhere in the cosmos. You could say we're all made of the same stuff, and that's true even without Wheeler's one-electron universe. We are all made of the same stuff, the same quantum fields, the same fundamental particles, all following the same laws of physics. So when you look at another person, remember, you're made of the same particles they are, the same particles that make up everything in the universe. You're not separate from the universe. You're part of it, a piece of the universe that's organized itself in just the right way to be able to look at itself and wonder. And that's what we're doing right now. The universe, through us, is wondering about itself, trying to understand itself. That electron field that fills all of space has gotten itself organized into brains, and those brains are thinking about the electron field. That's remarkable. That's wonderful. And Wheeler's crazy idea, even if it's wrong, helps us see that wonder. It helps us see that the universe is stranger and more beautiful than we might have imagined. So is there only one electron in the universe? Probably not, almost certainly not. But thinking about the question, working through the implications, that taught us something real about how nature works. And in science, that's what matters. Not whether you're right, but whether you're learning. And we're still learning. Maybe someday we'll understand why all electrons are identical. Maybe we'll understand the matter-antimatter asymmetry. Maybe we'll develop an even better way of thinking about particles and fields and time. Or maybe, just maybe, somebody will come up with an even crazier idea than Wheeler's one-electron universe. An idea so wild, so unexpected, that it makes the one-electron universe look conservative by comparison. And if that happens, if some young physicist somewhere has a crazy idea, I hope they pick up the phone. I hope they call someone and say, I know why. Whatever it is, because that's how we make progress. Not by being careful and conservative, but by being bold, by asking what if, by following ideas wherever they lead, even if they lead somewhere crazy. Wheeler did that. I did that. And you can do that too. The universe is waiting to surprise us. And maybe, just maybe, the next big idea is going to be just as beautiful and crazy as the idea that there's only one electron in the universe.